For our last talk, we'll return to the banking sector, but with a focus on a specific use case. I'm pleased to welcome Clara Higuera Cabañes, lead data scientist, and Javier Hernández, senior data scientist, both from BBVA. Please welcome them, and thank you.
Hello, thank you so much for having us. We are very happy to be here. I'm Clara Higuera, and my colleague who will be presenting with me, Javier Moral. We are data scientists at BBVA AI Factory. BBVA is the second largest bank in Spain, and we have a lot of presence in South America and also in Turkey. And the AI Factory, where we work, it's an area where data scientists, engineers, and product experts work together to solve business needs through building data products. From business needs or business problems like recommender of products or fraud detection, or the area or the field that we're going to cover today, which is debt collections. So I'm going to give a bit of an overview of what we're going to talk today, which is actually our own journey from approaching a problem from a predictive machine learning perspective to move to a causal ML approach, and why and how we did it. So we're going to explain the problem. We're going to explain how we approached it from the predictive ML approach, then how we approached it from the causal ML approach, and what the advantages and the limitations that we surpassed from the previous approach, and then our own lessons learned, so maybe they can be helpful for you in your use cases. So the problem that we solve is a quite classical problem in debt collections. So we do analytics on people that have already contracted some debt with the bank, like loans, mortgages, or credit cards. And unfortunately, sometimes customers face difficulties and they start not being able to pay or miss payments, and they go into default. So usually financial advisors, what they do is they do analysis on how to come up with solutions to minimize loss and also help clients. And there are a variety of solutions, financial solutions. And one of them is when the bank is willing to take on part of the debt of the customer if the customer commits to repaying the remaining debt in a single payment. So in this process can have an outcome of like success or not success. So success would be when the customer can repay the rest of the loan. So this is the general way of working. When the problem came to us, so we were asked to build a model that recommends the percentage of partial loss that can be offered to the client. And also, as in the previous talk, the financial advisor will be always the final decision maker. I have to say that this use case is still in a research phase, but we have done all the end-to-end and come up with very insightful results. So our goals are, first, can we find the optimal percentage per client according to probability of repayment success? And second, can we understand the effect of this percentage of assuming partial loss by the bank on repayment success by the customers? What is the data that we have? We have only historical data of these solutions offered by financial advisors to customers. So the journey is the client is having difficulties, then the financial advisor analyzes the situation, offers the solution, and then we can see whether there was a payment success. So one important thing is that we only have observational data. We could not make experiments, so they don't come from a randomized control trial. We have very, very few observations, 8,000 samples only, and our data is high dimensional. We have a lot of variables, up to 400 features that we have to decide which ones are the most important. The outcome is binary, like the customer was able to pay or not, and the treatment is continuous. So from now on, I'm gonna describe the treatment as a percentage of discount within a specific range. And is continuous. And there is no non-random allocation. So the majority of similar customers assigned similar treatment. So we think that we are facing a kind of cognitive bias by financial advisors for this fact. So on the plot, you can see the empirical data. So the buckets of percentage of discount on the x-axis, and on the y-axis the observed success rate. And one thing that we can see is that we can observe there is not much difference between like low percentage and high percentage. And we'll talk about that a bit more later. So we started this problem from a predictive ML approach and see where we got where it got us. So in-depth collections, we have a ML pipeline that we have optimized to usually for classification problems that we reuse. And in this case, so the first step is feature selection. We have a lot of variables, so we want to find the most relevant ones that have the most predictive power. And for this, we do an iterative process using methods like recursive feature elimination or permutation feature importance to reduce that set. So once we have these variables, we fit an ML model to learn the outcome using these selected features and also the treatment or the percentage. Afterwards, in order to calculate we calculate the outcomes for all customers for different treatments, or we do several different inferences with the model for all clients and different levels of treatment. And with this, we calculate the curves in the validation set. So because we have a continuous treatment, we can calculate those curves, that those values can then be included in a cost function to optimize that percentage. So the results that we found we got was first that treatment was not one of the variables that our selection method found as most important, but we still included it. We trained three different methods: logistic regression, XGBoost, and a neural network. And here on the left, you can see the percentage of discount and the probability of success, and we can see similar results as the empirical data. And also, if we calculate the marginal effect curve, that makes the difference between one percentage, for example, 30% and 25%, the probability of success is it's almost zero. So this is counterintuitive. It's and also business experts say it's not possible, that this doesn't have any effect. So we are probably here having a problem or a confounding bias problem that is distorting the treatment, the effect of the treatment on the outcome. And so we move to a causal ML approach for 4 reasons. One, we don't have experimental data. We couldn't make experiments because it would be unfair to offer different percentages to similar customers. We need to address this potential confounding bias in our data. We want to estimate and understand the effect of treatment on payment success. And we ultimately also want to generate unbiased counterfactuals with different treatment percentage, so we can get to that personalized percentage. And so we want to make decisions, and we're not so much interested in very accurate predictions. And Javi is going to tell you now about the causal ML pipeline that we have created for this problem.
Okay, thank you, Clara. So, what steps do we follow when facing this problem under causal ML? We've developed a pipeline that goes through the essential building blocks of causal inference, but also addresses the technical challenges of our data. So we start with our observational data and the domain knowledge provided by our financial advisors. And the first thing we do is dimensionality reduction. We focus on selecting the most important futures and removing the noisy ones. And this step has some similarities with the future selection step Clara has told us. But the idea is different, since in this case we're searching for a subset of confounder candidates. So the obvious question is why you do this step instead of throwing all your data set into a causal discovery algorithm and get the confounders from there. So there are two reasons. The first one is that we've tried to do so with many different algorithms and open source packages. And in most cases, they either run out of memory with 400 futures, or they last 20 or 25 hours to provide us results. And second, in the few cases we managed to get these results, we had to analyze 400 nodes and all the connections, so it was almost impossible to see if the graph has any business sense or to validate all the edges. So, given these two problems, we thought it was a good idea to first reduce this subset of futures and then try some causal discovery. And that's our next step. We ran 3 methods in parallel and we combined all the results in one single graph. And then we apply domain knowledge. We redirect some edges, remove some others, or even force some connections in the algorithm priors that we know they are happening in the real data generation process. And once we have our graph, we are ready to transform our causal effect estimation problem into a statistical estimate. We do so by obviously looking at the graph and getting the variables we need to control for, also known as the adjustment set. Then we're ready to estimate the causal effect. And here it's very important to remark that not all estimation methods are suitable for our case. Why? Because we have a continuous treatment. And most well-known estimation methods are more oriented towards binary or multi-class treatments. So in practice, we tried as many methods as possible, but we've just selected 3 of them for this presentation, which are backdoor regression, an S-learner, and inverse probability treatment. Then we apply as many refutation techniques as possible, but to check the robustness of our estimations and see the sensibility. But again, for simplicity, we will just discuss 3 of them today. And finally, we've come this far to make the best possible decisions. In our case, these are personalized decisions, as we want to get the optimal discount for each customer. So we generate counterfactors with our causal model, and then we apply a cost function to see the optimal discount for each case. So now I'm going to explain some of these steps with more detail. In this case, I will focus on the dimensionality reduction block, as just mentioned. So the first question to ask here is what kind of variables we aim to select under a causal ML perspective. We're looking for confounders. And a confounder, as you know, is a variable that influences both the treatment and the outcome. So they must be included into the adjustment set if we want an unbiased estimation. But why only confounders and not other kind of futures as strong predictors of the treatment or mediator variables? Basically because we will be adding high variance and selection bias to our estimates. Mateus, who has given a talk on Stream 1, has a lot of work on this field, with many examples demonstrating that only strong predictors of the outcome and confounders should be added to the adjustment set. So I take this opportunity to thank Mateo for his work, because it has saved us a lot of time. Okay, now how do we go from 400 futures to 20 futures to a reduced subset of confounder candidates? We do it in 3 steps. First, we define a model where we regress the outcome against the treatment and the covariates, just as in the predictive ML approach. We apply the same technique for future selection with 2 differences. The first one is that we force the treatment not to be removed at any future selection iteration. And why so? Because we know that the treatment is a strong predictor, is a weak predictor of the outcome in this case. So it would be removed, as we've seen. And second, because we know there are some variables that gain predictive power when interacting with the treatment. So if the treatment is removed, these variables will also be removed. Second step, we do the same, trying on regressing the treatment against the covariate, and we got another subset. And the third step is just to join both subsets in a final candidates selection. And with these 3 steps, we go from 400 futures to 20 futures. This means that the majority of our data set was noisy, and so it made sense to us. And then we ran 3 causal discovery algorithms, Peter Clark's, fast causal inference, and Lingam. And as I said, we combine the results and we apply some domain knowledge. And then we apply backdoor criterion to get the variables we need to control for. And that's how we get to this graph. This is a summarized version, as there are some features that only influence the treatment or only influence the outcome that we are not displaying here. There are just 5 confounders. And here one of the most surprising results is that just 2 of these outcome confounders were selected under the ML approach. So we were not controlling for the right variables under the ML approach, predictive ML approach, sorry. Then before looking at the estimation results, we want to look at the confounders distribution. What we've done is to split our confounders in different stratas and look at the treatment and outcome distribution for each strata. In this case, we have the stratas on the x-axis and the treatment distribution on the y-axis. And we can see, for example, this variable, loss percentage estimation, it represents a pre-calculated percentage of the unpaid debt amount over the total debt amount of past customers. So, for example, a value of 80% means that similar customers to the current customer lost the 80% of the debt when they were in default. If we take, for example, in this case, values between 90% of loss percentage estimation and 100, which is a lot of unpaid amount, we can see that the discount values are higher than if we look at the values below 90%. This is intuitive, as our advisors are looking at this variable to give the discount. The same happens with the number of years in default. The higher the number of years in default, the higher the discount given. So this is a confirmation of the non-random allocation of the treatment, as we can clearly check that our financial advisors are driven by these features. But to confirm if they are also a source of confounding bias, we must look at the outcome distribution. So that's what we do here. We control for some treatment levels, and if we look again at the loss percentage estimation, we can see that the higher the loss percentage estimation, the lower the success rate. So this is also intuitive, and the higher the number of years in default, also the lower the success rate. So now that we have our adjustment set, we are ready to estimate the causal effect. We apply the 3 methods I've mentioned before: backdoor regression, S-learner, and inverse probability treatment weighting. And we have the dose-response curve, which is the same as the effect curve Clara showed you, and the marginal dose-response curve, which would mean the effect under a continuous treatment. So, the most important result here is that under the 3 methods, we see a positive effect of increasing the levels of discount on the probability of success. This is intuitive and aligned with the domain expertise on the ground, and it contrasts with the flat effect we saw under the predictive ML approach. Then, once we've got our 3 estimates, we want to evaluate them. What we do is to apply some refutation methods to check, to validate these estimates and check for the robustness and see which one of these 3 is more reliable. Here we use a simple technique that is placebo treatment replacement. We replace the real treatment with a random treatment that follows the same distribution. We re-estimate the effects, and the desired result is that it goes to 0, and that's what happens. So good news. Next one is random common cause. We add random variables to our adjustment set. We re-estimate the effect, and it should keep the same, and that's what happens. So this is good news. And finally, we do some sensitivity analysis. We use values to quantify how strong an unmeasured confounder should be to neutralize the estimated causal effect. So our results show that the potential unmeasured confounder should increase the likelihood of both the treatment and the outcome by 31% to neutralize the effect. So this gives us like some proof that our estimation is robust, as no other confounders has such an association with our treatment or our outcome. And given all these refutation results, we choose backdoor regression as our model because it has a greater E-value, and it was the one who has a flattest marginal effect. And now Clara is going to explain how we use counterfactuals.
So once we have a causal method, which is of our preference, we want to get to that percentage that can be personalized for each client. And here we have calculated counterfactuals for 2 clients that are very different. So these are the variables, the confounding variables. So the first customer has been in default around 4 months. He has been, or they have been in the bank for 5 years, and the total debt amount is very low, 400 euros. The percentage of discount was 38%, and he actually, or they actually could pay after this solution was offered. If we go to the curves, the green point represents the percentage of discount offered to this client, and the causal dose response curve for this individual shows us that if the percentage of discount had been a little lower, the probability of success wouldn't have changed that much. The second customer, though, their state or financial state is much more deteriorated. They have been in default for 11 years and in the bank for 15 years. And the debt is quite higher, $83,000 or euros, sorry. And the percentage of discount was 71%. If we look at the curve, we can see the red dot, which represents the discount offered in reality or in the past. If we look at a lower percentage of discount, we see that the success, the probability of success is lower. But also, if we move to the other end, to higher percentage of discount, the probability of success doesn't increase that much. So these type of results are very insightful and can be used in 2 ways. First, to give this information to financial advisors, so they can better decide what is the solution or the percentage that they would like to offer with these counterfactuals, and also these values of these curves can be used in a cost function to compute the percentage per client. I think we're running out of time, so I'm going to be quickly here. So we're wrapping up, and for us, moving from predictive ML to causal ML have had the 3 main advantages. We have addressed confounding bias, we have started to understand the effect of treatment on outcome, and found causal variables for business insights. So now with those confounding variables, also business and financial advisors can also tailor solutions, and we have built counterfactuals to optimize the percentage of discount for these offers. And so here we have also a table of comparison, and the one thing that was better predictive ML was in accurate predictions. So as we said, this is not so important now in this problem, because we want to make like sound decisions. And just to wrap up our lessons learned, we have found that causal ML has actually helped us to solve the problem where solely predictive ML approaches couldn't solve it. We have invested, as Javi said, a lot of time in causal discovery, along with talking with business experts in coming up to those confounding variables. Most of the known estimation methods are more oriented to binary treatment, and we had a continuous treatment, so there is still a line of research and work to be done there. Explainability, which is something that causal ML is good at. It's very important for us because of the highly regulated industry, and also because explainability is good anyway for customers and financial advisors as well. And lastly, like a cultural conclusion, which is comparing these 2 approaches have helped us introduce causal ML into the company, because we were more used to predictive ML, but by this comparison, we can see the advantages. So, thank you very much.
Amazing. Thank you both. We do have a couple of questions, if that's okay. First one, are you reducing the features using a lasso regression in steps 1 and 2?
No, we're using an in-house methodology that combines permutation feature importance and recursive feature elimination. It's iteratively. So we rank the features first, and we try to remove subset of features iteratively.
Amazing, thank you. Second question and final question. In your predictive ML model, do you treat the treatment variable in the same way as other features?
No. In the predictive, you mean the predictive ML approach? Yeah. No. We treat it the same way. So it's removed and we add it at the end because otherwise we wouldn't be able to do interventions or estimate the effect. But yes, it's like in the first step, it's the same as other features.
So we included as in both approaches the treatment as a percentage.
Amazing. Clara, Javier, thank you very much.
Thank you.